In this segment, we will talk about the basic notions pertaining to systems of linear equations. Let's begin with a single linear equation with two variables. For example, suppose we are looking at the following linear equation: x minus 2y equals to 4. This is a linear equation with two variables, two unknowns, x and y. A solution of this equation is a pair of numbers such that when we substitute these numbers, one for x variable and the other for y variable, we obtain a correct equality. For example, the pair 0, negative 2 is a solution of this equation because if we substitute x equals to 0 and y equals to negative 2 into our equation, we obtain a correct equality. 0 minus 2 times negative 2, it's supposed to equal to 4, and it is equal to 4. In the pair of numbers that we're looking at, the first number is the value of x and the second number is the value of y. On the other hand, if we look at the pair 0, 3, this pair is not a solution. This is because if we substitute x equals to 0 and y equals to 3 into our equation, we get something that is not a correct equality. 0 minus 2 times 3. This is supposed to equal to 4, but it's not because the left-hand side actually equals negative 6. The first thing to realize about linear equations in several variables, two or more, is that they have infinitely many solutions. Why would that be the case? Well, let's go back to our equation x minus 2y equals to 4. Note that we can actually select the value of x arbitrarily. For example, if we select x equals to 5, I can plug that value of x into the equation to get 5 minus 2y equals to 4. And then we can solve for y, the resulting equation. In this case, we're going to get 2y equals 5 minus 4, which is 1, and so y would have to be equal to 1/2. And so by doing these calculations, we obtain a solution of this equation with x value equal to 5. 5 comma 1/2, this pair is a solution of our equation. Now, I chose x equals to 5 arbitrarily. We didn't have to start with this value. We could start with a different value of x, and we would be able, again, to find the appropriate value for y that would make the pair, the value of x and the value of y, to be a solution of that equation. For example, let's start this time with x equals to negative 2. If I plug this value into the equation, I'm going to get negative 2 minus 2y equals 4. And we can solve this equation for y to obtain 2y equals 2y equals negative 2 minus 4, negative 6. And dividing by 2 both sides, we find that y equals negative 6 over 2, negative 3. And so starting with the value of x equal to -2, we obtain a solution -2, comma, -3. Okay, now the key is that we can start with any value of x and obtain a solution with that value of x. Therefore, since we have infinitely many possible choices for the value of x, we can find infinitely many solutions to this equation. In fact, it's very helpful to look at this situation graphically. If we begin plotting these solutions in the xy plane, each solution will be represented by a point, and when we plot all of these solutions, we obtain the graph of this equation, which will be a straight line. Let's take a look at this graph. So here I used a graphing calculator to graph the equation x minus 2y equals to 4, and we see that the graph of this equation is a straight line. In fact, this is why the equation is called a linear equation. That is because the graph of the equation is a straight line. Each point on this line represents a solution of the equation. For example, we see here the solutions that we found: 0, comma, -2, -2, comma, -3, and lots of other solutions in addition to the ones that I mentioned. Likewise, any solution of our equation represents a point on this line. And so this gives us a great visual representation of the solutions of our equation. Now, let's add another linear equation to the one that we've just considered and look at the system of linear equations. So I will rewrite our first equation, x minus 2y equals to 4, and I'm going to add another equation, linear equation in x and y variables, namely 3x plus 2y equals 6. So now we have a system of two linear equations. And what does it mean to say that we are looking at a system of two or more equations? When we're solving a system of linear equations, we want to find the values for our variables, in this case x and y, such that when we plug them into all equations in the system, all of them turn into correct equalities. In other words, when solving a system of linear equations, or in fact, system of any equations, we are trying to satisfy all equations at the same time. Now, if we look at the second equation in this system by itself, then we would find that it has infinitely many solutions, and the graph of that equation is again a straight line, and each point on that line represents a solution of the equation. Let's again look at the graph of the second equation. It can be graphed just like we graphed the first equation. I'm going to pull up my graph, and I'm going to add the second line here. 3x plus 2y equals 6. So here's our second line, and the first, let's remember that the points on the first line, the red line, represent solutions of the first equation, whereas the points on the second line, the purple line, represent the solutions of the second equation. But we are this time looking for solutions of the system. We want to find points that satisfy both equations at the same time. And of course, that would be the point where these two lines meet. In fact, this is a graphing calculator, and I can hover over this point and it will show me what that point is. We see here that x is 2.5 and y equals negative 0.75. That is the point where these two lines meet. And this pair of numbers is actually the solution of the system. Let me now show you how one can find this point of intersection algebraically without graphing the equations. The idea of solving the system algebraically is actually fairly simple. We can manipulate our equations so that one or more variables get eliminated from our equations. For example, let's notice that in this system, the first equation contains the y term negative 2y. I'm going to highlight it in yellow. In the second equation, the y term is positive 2y. So if I add the first and the second equations together, then the y terms will cancel out. E1 plus E2. E1 plus E2 indicates what an operation that I'm performing on these equations. I'm adding equation 1 to equation 2. I add the left-hand sides of these two equations together, and I get 4x. And I add the right-hand sides of these two equations, 4 plus 6, that gives me 10. Observe that we have eliminated y variable from the second equation, and we obtain now an equation that contains only x variable. This allows us to solve for x. We get x equals to 10 divided by 4, which in fact is 2.5. We could also write 5 halves. Once we found the value of x, we can plug it into either of these two equations and then solve for y. Let's, for example, plug in the x value of 5 halves into the first equation in the system. Then we find that 5 halves minus 2y equals to 4. And we can now solve for y. 2y will have to be equal to 5 halves minus 4. Or after making a common denominator, 5 minus 8 over 2, which is negative 3 halves. And now dividing by 2, we find the value of y, which is negative 3/4, or negative 0.75. And that is our y value. We found the solution of our system, 5 halves, comma negative 3/4. Note that the system has no other solutions. We found the value of x. It has to be equal to 5 halves. We have no other possibilities here, and the value of y has to be equal to negative 3/4. Again, we have no other possibilities. And the fact that the system has only one solution is also confirmed by graphing the equations. We see that the two lines meet at a single point. Now, let's talk a little bit about the possibilities for a system of two equations with two unknowns, or 2 by 2 system. what are the possibilities in terms of how many solutions the system may have. In this example that we've just went over, the system has a unique solution, just one solution. Two lines meet at a single point. We say in such cases that the system is independent. Independent system is a system that has only one solution. Now, it is possible for a system to have many solutions, in fact, infinitely many solutions. And it is also possible for the system not to have any solutions. It is quite easy to see this graphically. So if we're looking at a 2x2 system, a system of two linear equations with two unknowns, basically we're looking at two lines, and we want to know what are the possible cases in regards to common points. How many points can two lines have in common? And the case that we've just considered is when the two lines meet at a single point, and that gives us a one solution to the system of linear equations, independent system. It is also possible, it is possible for the two lines to be parallel, right? If the two lines are parallel, then they do not meet anywhere, and the corresponding system of linear equations will have no solutions. We say in such cases that the system is inconsistent. Inconsistent system has no solutions. Let me quickly give you one example of such system. So for instance, let's take our first equation to be exact same as before, x minus 2y equals to 4. And now let's take the second equation to be x minus 2y equals to 6. It is clear that the system has no solutions because x minus 2y cannot equal 4 and at the same time equal to 6. If we graph these two equations, we obtain two parallel lines. Now, it may seem to you that this covers all the possibilities, but strictly speaking, there is one more possibility, and that is when we graph two equations, we get exact same line. So the two lines may actually coincide. I will represent this by making one line thick. In this case, when the two lines coincide, they have infinitely many points in common. In fact, any point on that common line would be common to both of our lines, and the system will be dependent. A dependent system has infinitely many solutions. Here's an example of such system. Let's take our first equation to be exact same as before, x minus 2y equals 4. And the second equation will be 3x minus 6y equals to 12. Now you probably noticed that the second equation here is exact same as the first equation multiplied by 3. And so if you graph these two equations, you're going to get exact same line, and any solution of the first equation is in fact a solution of the second equation and hence of the system. Okay, so this covers all possibilities for a system of two equations in two unknowns. The system may be independent, inconsistent, or dependent. As we will see later, exact same three alternative possibilities occur for any system of linear equations with however many equations and however many unknowns. Let's next talk about equations in three variables, and let's start again with a single equation and three unknowns, such as x plus y plus z equals to 2, for example. Just like an equation with two unknowns, this equation will have infinitely many solutions. For example, we can have 1, 1, 0, or we can have 0, 2, 0, or we can have negative 1, 1, and 2. All of these triples of numbers are solutions, and it's very easy to find more. In fact, we could choose x and y values arbitrarily and then plug them into this equation, and determine the value of z that would make this equation work. Graphically, we can, just like graphing an equation in two variables, we can graph the equation in three variables, except that this time we will have to do the graphing in three-dimensional space, which has three coordinate axes, x, y, and z. Here's an example of this graphing. I can pull it up. Okay, here. I used the computer algebra system to graph this equation, and you can see that the graph of this equation, x plus y plus z equals 2, is a plane in three dimensions. I'm going to rotate this plane so that you could get a sense of how it looks and how it's positioned in three dimensions. Again, every point on this plane represents a solution, and every solution represents a point on this plane. Very good. So now let's add another equation in three unknowns to the one that we've just considered. X plus y plus z equals to 2. This is our first equation, same as before. And I'm going to add another equation in three unknowns, 2x minus y minus 2z equals to negative 2. And this is a system, meaning that we would like to find the values of x, y, and z that satisfy both of these equations at the same time. Now, again, graphical representation tells us a lot about what we should expect in terms of solutions in this case. The graph of the second equation is going to be another plane in three dimensions. And when we're solving the system, we're solving for common points. In other words, we're looking for points of intersection of these two planes. Here I graphed the two equations together in the same coordinate axes, in the same coordinate system. And you see the orange plane that we had seen before, and now we have a second plane which is in blue, and the two planes meet along a line, and each point of that line represents a solution of the system of the two equations together. since there are infinitely many points on this line, we see that our system of 2 equations and 3 unknowns in this particular case has infinitely many solutions, and so it is a dependent system. And let's find some of these solutions algebraically. So I'm going to write here that this is a dependent system. It has infinitely many solutions. In fact, those solutions fill in a straight line. Now, this time I can't select the values of x and y arbitrarily to obtain solutions of the system. Why would that be the case? Well, let's try. So for example, if I try x equals 0 and y equals 0, and I plug it into the 2 equations in the system, the first equation was going to turn into z equals to 2. And the second equation is going to turn into negative 2z equals to negative 2. And solving the second equation for z, we obtain z equals to 1. Now that contradicts the above equation, which says that z must equal to 2. This is a contradiction. So this tells us that there will be no solution of this system with x value equal to 0 and y equal to 0. And it is apparent that we are not able to select the values of x and y arbitrarily. But perhaps we could choose the value of x arbitrarily. What if we just what if we select the value of x equal to 0 and we say nothing about the y value at this point? If x is equal to 0, then substituting x equals to 0 into our 2 equations, we find that y plus z must equal to 2, and negative y minus 2z must equal to negative 2. Now, this is a system of 2 linear equations with 2 unknowns y and z, and we can try to solve it. Adding these 2 equations together, we will eliminate the y variable from this equation to obtain negative z equals 0, and therefore z must equal to 0. And substituting z equals to 0 into the first equation in this 2x2 system, we get y plus 0 equals to 2, and therefore y must equal to 2. And therefore we found a solution of our original system of 2 equations with 3 variables, namely 0, 2, 0. Now, as an exercise, choose a different value of x. For example, x equals to 1 or x equals to negative 2, and do the corresponding calculations to find y and z. You will see that choosing these other values of x and of x, 1 or negative 2 or any other number, you'll be able to find the corresponding y and z values that would, when taken together with the value of x, would give us a solution of the system. Okay, now let's throw in another equation into this system and consider the following system: x plus y plus z equals to 2. The first 2 equations will be the same as we earlier considered. Second equation, 2x minus y minus 3z equals negative 5. And the third equation this time is going to be, the second equation is 2x minus y minus 2z equals to -2. And the third equation will be 3x plus 3y plus 2z equals to 3. Okay, and so now we have three equations that we want to satisfy. And again, looking at the graphic representation of the system gives us a lot of insight into what we should expect about solutions. Let's look at the graphs of these equations. In the next picture, I added the third plane, the graph of the third equation. And so now we have an orange, a blue, and a green planes. The blue and the orange planes intersect along a line, and that line meets the green plane at a single point. Let me rotate the picture a little bit so you could observe the situation. We see that these three planes meet at a single point, and therefore we expect our system to have a single solution. That system will be an independent system, and let's see if we can find algebraically what that point is. The idea is exact same as before. We would like to manipulate the three equations in our system so that variables get eliminated. In principle, we can eliminate variables in any order. We can choose to eliminate x variable first, or we can choose to eliminate y variable first, or we can start with the z variable first. What variable is being eliminated first depends on which is easier. You could eliminate x or y or z variable first. It is possible always to eliminate any of the variables first. However, the calculation may be slightly more or somewhat more complicated in one case compared to the other. Now, in this case, we can see that a z variable can be easily eliminated from the third equation. So I'm highlighting here the z terms. You can see that the second and the third equations have the z terms that make elimination of z variable from the third equations very easy. All we need to do is add second equation and the third, and that would eliminate z variable from the third equation. It is also not difficult to eliminate z from the second equation. And so let's begin by eliminating the z variable as much as we can. So I'm going to eliminate z variable from the third equation first by adding to that third equation the second equation. For each step, I indicate what that step is or does on the left-hand side by writing, for example, for the third equation of the new system that I'm about to write, E3 plus E2. What that means is that the equation that I'm going to write in that space next to E3 plus E2 is simply the sum of the third and the second equations from the previous step. And we get 5x plus 2y. The z term cancels out. Negative 2z plus 2z is 0. And on the right-hand side, we will have 1. To eliminate z variable in the second equation, we can add to the second equation first equation multiplied by 2. E2 plus 2e1. And that gives us 4x plus y equals 2. Let's rewrite our first equation with no changes. X plus y plus z equals to 2. And so what we have accomplished here is we have eliminated z variable from the second and the third equations. And now if you look at the third and second equations together, they form a 2x2 system of two linear equations with two unknowns x and y, which we can solve as we had done above. Let's do that. There are multiple ways in which one can proceed. One way is to eliminate y variable in the second equation by multiplying it by 2 and subtracting from it the third equation. I'm going to rewrite the first equation. I'm going to replace the second equation with twice the second equation minus the third equation. That's going to give us 3x. The y term will cancel out, equals to 3. Equation 3 I will simply rewrite. 5x plus 2y equals to 1. And now the second equation contains only x variable. We can solve for x in that second equation to find x equals to 1. Once we found the x value, we can plug it into the third equation and solve for y. 5 times 1 plus 2 times y equals to 1, and therefore 2y equals -4 and y equals to -2. Once we have the x and y values, we can plug them into the first equation, and then we can solve for z. We get 1 plus -2 plus z equals 2, and from here we find that z equals to 3. We obtained the values for all of our 3 variables, and we found that our system has a single solution, which is the triple 1 for x, -2 for y, and 3 for z. And this, of course, is the point in which the 3 planes meet, the 3 planes that we graphed earlier. Right here, the blue, orange, and green planes meet at a single point, which we had just calculated. This is the point 1, -2, 3. Now, to conclude this video, let's talk about the possibilities in terms of the number of solutions for a 3x3 system. We find that exact same alternative possibilities can occur as in the case of a 2x2 system. The first possibility, the first case, is an independent system, in which case the system has a unique solution, one solution. This happens when the three planes, which are the graphs of the three equations, intersect at a single point. And this is the picture that represents the situation. Another case is that our system may have no solutions at all. That would be an inconsistent system. And this can actually arise in somewhat different ways. Here is a situation where the three planes intersect each other in such a way that every pair of planes intersects along a line, and the three lines of intersection corresponding to the three pairs of planes are all parallel to each other. Therefore, the three planes altogether do not have common points. It is also possible for our three planes to be parallel, or two of the planes to be parallel, and then the third plane would meet the first two planes along lines which are parallel to each other. And finally, the third case is a case of a dependent system, in which case the system has infinitely many solutions. This occurs when the three planes intersect along a single line, as pictured here. And there is actually another case that I did not picture here, and that is when three planes actually when they actually coincide, when the three planes, when the graphs of three equations are actually the same plane. Okay, this concludes our introductory video on the basic notions for systems of linear equations.